Something. Algorithm. Okay. So we were until now. अब कोई है नहीं कर सकता 50 मिनट बाद आएगा तो क्या कैसे ट्रैक होगा इस लिख दो ग्रुप पे जो और लिंक भेजना नहीं है क्योंकि इसके बाद पढ़ाएंगे या एडमिट करते रहेंगे बैठ के ठीक है So, uh, with that, first of all, we have to understand that whether the complex or a compound, whether form or there can be something which, because of which it is not a form. So, you can see that like you take a metal and you put typically you cannot expect that compression. There has to be certain chemical as well as bonding perspectives, bonding criteria, because of which a chemical compound is formed, or because of which any compound, let us say, may it be organometallic, may it be inorganic.
Excuse me, sir.
Hello?
Sir, we are not able to hear anything.
Huh? What happened?
Sir, we are not able to hear anything.
Maybe I have to talk here. Okay. Okay, let us see whether it works because I am taking offline class. So with that, I don't know how do I manage because it is I don't know. Okay, anyhow, let us see. Now, are you able to hear?
Yes, sir, better.
Okay,
Yes, sir.
fine. So I have to be here for the. So basically, with that criteria, we need some guidelines. As for example, until now, for organic compound, for example, like a four annulenes are not stable. Like that, in inorganic chemistry also there are certain guidelines which dictates whether a compound has to be stable or not. So that is called 18 electron rule. So okay, by the way, I should tell that I will share this PDF also for your convenience because of this technical problem. If there is any you won't understand all of these things, you can read the PDF also. Okay? Fine. So the 18 electron rule is actually characterizing and predicting the stability of the bases. Then why the 18 and the question next comes why the 18 electron rule is important. Why not it is 16 electron rule? Why not it is 14 electron rule? Why not it is 20, 22 electron rule? Why it is always 18? Huh? Be louder because I cannot come to you. Yeah. More stable. But why more stable? Due to
Sir, it achieved noble gas configuration.
huh? Why?
Sir, it achieved noble gas configuration, that's why.
Yeah, 18 electron. If it is a element, then it will attain a noble gas configuration. That is fine. But in a compound where molecular orbitals are involved, there somebody has switched on their own.
Rajat, please switch off your mic.
Everyone, please switch off your mic. Yes. Okay. Yeah. Somebody was telling something. Yeah, noble gas configuration. Yeah. In case of molecular orbitals, when the molecular orbitals are involved, at that time, how do you explain it? The idea is same. Idea is basically the same. That in every case, if the octet is not filled or 18 of the valency electrons are not filled, if there is a vacancy in the last cell, then definitely some electron can be taken or some electron can be donated, and that will involve the reaction of that particular complex. Correct? So, yeah, yeah, anti-bonding pi. But that is for CO. If in case of, for example, if it is a molecular like a octahedral complex, then it will not enter into the anti-bonding level. Then it will be all remaining within the bonding, even not the non-bonding. That is written here. You see? Uh, correct. Correct. In 18, correct. That is correct. But that does not. That's why the CO have a additional electron which can be donated, and in the return of the donation, it can get the back donation from the metal to have a pi star bonding, right? That's why it is reactive, right? So, like if there is a reactivity, there has to be a reason from the molecular orbital perspective, as I said, right? But in case of a complex, whether it is coordination, whether it is organometallic, in that case, for example, valency cells of like a metal will be having 18 electron, 2 in each of the 5 d orbitals, 2 in each of the 3 p orbitals, and 2 in the s. Yeah, I mean, CO maybe not the you take NO, then in that case it will enter. NO is like take anything suitable, then it will enter. In case of ligands, in case of like a coordination compound, it will not enter because of this. How can it enter? Because you have the vacancy of that much. If provided, if all the like orbitals of the metal are involved, for example, like all the 5 d orbitals are involved. That means like when these 5 d orbitals will be involved in case of octahedral geometry. Now, again, actually, correctly you said one thing, that if now I involve a tetrahedral complex where all the d orbitals are not involved, then what happens? For example, dz square in a tetrahedral complex, or better to say square planar complex, will not be involved. Right? Square planar complex means everything will be in the x, y, z, x and y plane. So dz square will be vacant. Then what happens? Question is this: what is the answer? Anybody from there? Answer is the same. You have to take care of the molecular orbitals. That means if your one of the orbital is not participating, you have to take out that electron from your number. That means in that case, it will be following Instead of 18 electron rule, 16 electron rule. Correct? Simple. Do you understand now? Exactly as you said, this is the case that in the case of participation of all the 5d orbitals, 3p orbitals, and one s orbital, that means altogether total orbital number is 5 plus 3 plus 1. How much? 9. So then you can expect 18 electron rule has to be followed. But if the complex is such geometry that the particular orbital is not participating at all, for example, square planar geometry, then the number will come down to 16. Because altogether there will be 4 d orbital, 3 plus 1. So 4 plus 3 plus 1 means 18. 16, right? So total will be 8 into 2 equals to 16. So then the total orbital, total electron count will come to 16. Exactly like that way it will go. I thought that I will tell it later, but as you already pointed out, it helps me a lot. Thank you. Okay. So basically, with that introduction, now we have understood why 18 electron is very much important for the stability of a particular compound. May it be coordination, may it be your organometallic compound. Now, let us see. Okay. Now let us see how. Good. Here. You all see, right? Fine. So now, if, for example, the 18 electron has to be counted for a complex, then you should know how a particular metal is giving how many number of electron and how many number of electron is now coming from the ligand. Because both the metal and the ligand can have electron, or it can also be, it is not a necessary criteria. Criteria is that you have to have altogether 18 electrons. But it can also happen that all the ligands are donating all the 18 electrons. Metal is not donating anything. Or it can be the other way around also. Correct? So that means you have to know how many electrons are coming from the metal and how many are coming from your ligand. So if that is the case, there are some ligands are actually given here, which are normally in a coordination compounds. You deal with the ligands like water, ammonia, right? Then what are the common ligands you know? Anything else? Huh? Water, ammonia, then what else? Chloride, bromide, halides, all of these things you are the ligands, common ligands. But in case of organometallic chemistry, the same thing we will extrapolate into little different kind of ligands. For example, these, which are nothing but basically the unsaturated ligands, you can say, or you can also say that they are will be having metal carbon direct bonds. Correct? So, for example, if this one is now will be having, then basically we have to go to metal. C bond of the R has to be created, and that because of that it will be a organometallic compound. Correct? Fine. Now, also it can have few ligands like a CO, CaCO. It can happen. That these are all also nowadays, as I said, taken care within this periphery of the organometallic chemistry. Fine. Now, basically, you have to also know there are particular denotation to say how a ligand is bound to a particular metal, right? For example, there can be a situation that the metals are bound by, there is a ligand which is coming, and in between the two metals, that ligand is remaining equidistant. That means it is bound with two metals. Or it can happen one metal is basically coordinated by many sites of a particular ligand. Correct? So these are all the possibilities can happen. So because of that, there are particular symbols are given for sorry. There are particular symbols are given for denoting how a ligand is bound. For example, hepto symbol. You see, here is hepto symbol. Is a numeric, basically superscript, or basically with that some numbers you have to be there, which provides a topological description by indicating the connectivity between the ligand and the metal, central atom. For example, if the 5 carbon atoms of a cyclopentadienyl, so what is cyclopentadienyl? CP is the nothing but cyclopentadienyl ligand, right? What does it mean? Can anyone draw quickly in your notebook and show me how is a cyclopentadienyl ligand can be there? Enyl means there will be anion, correct? So can you draw cyclopentadiene? Cyclopentadiene. Draw in your notebook cyclopentadiene first, and they put an anion and show me how it will look. Chop. So, for example, cyclopentadiene is how much? How it will be looking? Cyclopentadiene, correct? Now I have to have an anion. Where the anion can happen? Here, right? So there it will not be remaining like that. Correct? Because why not? How many electrons? 6. So 6 means it is aromatic or anti-aromatic? Aromatic, right? So it will attain aromaticity. So because of what? Because of that, it will, instead of the charge being localized, it will be fine. This is cyclopentadienyl ligand. And now you see that previously there was, if the charge would be here, then the binding would have been very prominent from this side. Found by this. Right? But now all the carbons of cyclopentadienyl are equivalent. Right? So how do you say that cyclopentadienyl will be found by only one?
So after bonding, any compound, if a compound is after bonding is becoming more unstable, it will ever show that type of bond.
Correct. That is also correct. That is also correct. That's what we will see. That's what the 18 electron rule is the guiding. For example, if the metal environment is like that, that after getting all the electron, it is going to 19 electron or 20 electron. What cyclopentadienyl will do? Then cyclopentadienyl, normally the bonding of the cyclopentadienyl is shown by this way. This is means it is bound with all the others. If instead of if I stop it here, then it is bound with the C1. If it is extended, given a circle which is basically aromatic, and if it is extended after some people, that means it is bound with all the 5 carbons to the metal. Now that means now let me tell you, if the 5 carbon is participated into the bonding, then there will be 5 electron donation from cyclopentadiene. Now, for example, if there is already 14 electron on the metal from other ligands and the metal electrons. So altogether it will then coming to 19 if it is so. But 19 is not a stable number. Then what it will do? It will deviate from its equivalent bonding scheme to rather for example it may go
Excuse me, sir.
yeah
Sir, can you use any kind of digital board or
no
something?
here we don't have. What can I do?
Okay, sir.
Okay, so yeah, correct. Now this will be maybe I just try to put it. This can you see? Yeah, I hope you can see that. Yeah. So basically, you see, now it will be bound with 4 of the carbon leaving this electron. Then instead of 5 electron donation, it will be 4 electron donation. 4 plus 14 will be 18. By this way, by the number of overall electron to maintain the number 18, right? Means the electron will overflow from the bonding orbitals, right? Any of the ligand will be twisted in such a way that basically overall thing should come to 14. That is basically the underlying overall thing. But now, before we go into that details, we will show some examples like that. Before we go into that details, we have to first understand that how we will calculate that 18, number 18, right? And that is the exercise for today. So now you see, there will be the eta. As I said, there is a eta, which, for example, number of the particular number of, it is called actually like a, yeah, with the numericals provide a topological description by indicating the connectivity between the ligand and the central atom. That means how many atoms of a particular ligand is bound to the metal. Fine. Then there will be also symbol like mu. Mu indicates bridging, right? Normally we have mu2, mu3, all of these bridging things. What does it mean? This means how many metals together are bound with that particular ligand. So mu2CO means, sorry, mu2CO means the CO ligand is now bound with 2 metals. Mu3CO means now the CO ligand will be bound with 3 ligands. Sorry, I am sorry. CO ligand will be bound with 3 metals. And here CO ligand is bound with the 2 metals. So the number of metals with which a particular ligand is bound is given by the symbol mu. Okay, now let us start calculating. Okay, before that I would go like how to know the number, correct. For example, these are different type of ligands might occur in your organometallic chemistry. And see how many electrons they are actually donating to the metal for bonding. If it is carbonyl, metal carbonyl, normally metal carbonyl donates 2 electrons. Then phosphine, then 2 electron, amines, 2 electrons. So all the neutral ligands, normally they are donating 2 electrons, except for example nitrosyl. Nitrosyl case, if it is linear, then nitrosyl will donate 3 electron. If it is bent, then nitrosyl will donate 1 electron. You have to remember these numbers, how many electrons will be coming from a particular ligand. Now for the anionic ligands, notice, what is the first anionic ligand here? Amide. Then hydrogen. Hydrogen is not hydrogen, it is hydride. Because hydrogen ligand is not possible. Hydride. Then next is, for example, alkoxide, OR minus. Then it can be, for example, alkyl, R minus. In all the cases, the charge will be the number. The charge will be the number, I repeat. For example, if there is a -1 charge, it will be giving you 1 electron. Correct? Okay. Then you see, correct. And yeah, next type of ligands are basically eta type of ligands. You see, in the case of eta type of ligands, eta number will give you the number of electrons being donated by a particular ligand. If it is eta 3, then usually it will be giving 3 electrons. You see, 3 electron. Eta 5 means 5 electron. Eta 6 means 6 electron. Like that. Carbine will be giving you 3 electron because it is metal carbon triple bond. Carbene will be giving you 2 electron because there will be metal carbon double bond. Thiolate, how many electron? Why so? Cyclohepta, where is cycloheptatriene? Yeah, right. Draw first the cycloheptatriene, and by this way, as I mentioned it here, you can draw it. So everyone draw the structure of the cycloheptatrienyl ligand. How this ligand will be? Draw it. Okay. So next question is that thiolate. Why thiolate is giving 1 electron? Because it is negative. Right? As I said, if it is charged, then the charge will be the number. Unless that is there is also kind of a mu2 type. mu2 means you have to consider charge in one side and for example, I give you an example. Yeah, what are your halides? Correct. Now you see mu2 chloride ligand basically, right? If it is normal chloride, how many electrons it will give? 1. But now it is mu2 chloride means how many electrons it will give? 3. Because normally it will give 1 for one particular metal, but now it is also bridging with another one metal. To that it will give another 2 electrons. So altogether 3 electrons. So therefore mu2 chloride will now be 3 electron donor, mu2, all these things. If it is mu2, then it has to give now 3 electrons. Now, for example, let me see. Yeah, but remember one thing. If it is mu2CO or mu3CO, all will give only 2 electrons. Why? Because CO have only 2 electrons. Right? It is having the lone pairs. That's why it can donate. But CO, all the others are actually bonding type electrons. Only the non-bonding electrons can participate into your bond, or can be donated to the metal. Right? But CO don't have more than 2 electrons in their non-bonding level. So there is no chance. That's why whenever CO is involved in the metal ligand bridging, those bonding will not be like a 2 center 2 electron, not in that way, or 3 center 3 electron will not be happening. Then it will be 3 center 2 electron bonding, 4 center 2 electron bonding. So multiple center 2 electron bonding is basically are called the banana bonds, correct? So this type of banana bonds are therefore very much common. Huh? That is the eta. Eta number is called the hapticity number. Right? It was written here. You wanted to ask something? कोई कुछ और पूछना चाहता है? ठीक, दिखाता हूँ. That will come again. We will revisit it here. Okay, so no issues. I just wanted to give you a feeling that how. Okay, now you see alkoxide. Here also one electron for the negative charge, another two is because of the coordination to the other side, right? So it is mu. If it is like a just given the mu means it is mu2. Remember it. If it is any number is not given, only mu written means it is mu2. Because if it is like if it is only one bound with only one metal, then there will be no mu. Mu means it has to be mu2, right? If it is mu3 or more, then you have to specify it. Correct? So that's why you see these are all the different terminologies will be used, and you have to understand that. So mu means in that case it is mu2, not the mu1. Mu1 means it is bound to only one metal. Then there is no need of mu, right? Once it is mu given, as you can see, once it is mu given, as you can see, in that case it must be mu2, right? And mu2 means, as I said, if it is negatively charged, then 3 electron donor. Okay. So these are basically there are two types of like a counting methods are there. One is called neutral count and one is called charge count. If you are taking the charge count, then these are the electron numbers. 3 into 3. Why so? As you can see here, for example, cyclopentane dienine. Cyclopentane dienine have now 5 sides for electron donation, right? So 5 plus there is a charge. So therefore there is 6 is taken by this way. But you will soon realize that charged electron count is little bit complicated than the neutral count. That's what neutral count is easy to follow. Of course, you can follow the charge count, but in that case, you have to be very cautious because charge count, as I said, is little bit tricky. Okay, I will show both of that now. Okay, so this is the thing. Now I go back to the particular example. Fine. Now, for example, I would like to ask you, what are the total electron number on the metal because of the coordination, right? Now you see, ruthenium by neutral count is how many electron donor? Remember, you just have to remember the whole periodic table, or basically at least the transition elements, right? Can anyone say all the transition elements without seeing anything? Start from group number like 3, scandium, yttrium, then lanthanum, correct? All of these things are there. Then basically next is basically titanium, then zirconium, then hafnium. Magnesium? No. I am talking like always whenever you are going to the group, you have to go by vertically. Horizontally, you can also go. That is not an issue. Like then it will be scandium, titanium, vanadium, then chromium, then Manganese, then iron, then cobalt. But in this case, the particular problem is that you are not getting the group number. That's what you have to remember the group number vertically. This is the trick, right? So go with it. Scandium, then yttrium, all of this thing is there. Then titanium, zirconium, hafnium, vanadium, niobium, tantalum, then chromium, molybdenum, tungsten, right? Then manganese, technetium, rhenium, correct? Then your iron, ruthenium, osmium, right? Then what is next? After iron, cobalt, rhodium, iridium, nickel, palladium, platinum, copper, silver, gold, zinc, cadmium, mercury. This is the way you have to remember it. Because then what will happen? You will be, once there is a metal, you know it is coming from this group. And immediately this number at the top, this number you can get immediately from the group number itself. You don't have to think. I see iron means I will put 8. Without thinking how what is its oxidation state, all of this. Because why actually the charge count is difficult? Because of the fact that you must be sure in a coordination compound it's rather easy to know what is the oxidation state of a metal. But in case of organometallics, because of the so many bonding schemes, it is sometimes very difficult to know what is the exact oxidation state of a metal, and that actually the complicates the counting. But there is also, that's why the neutral counting is there. Neutral counting means you just have to remember that group number of a particular metal. Iron means without thinking anything, I will put 8 first. Fine. So 8 is there. Then I put mu3, hepta3 allyl. Right? Hepta3 allyl. Hepta3 means, again, you don't have to think. Number 3. Because hepta3. Correct? So 3 electron is coming. Then PPA is 3. H should be not subscript. PPA is 3. So PPA is 3 means each of the PPA is 3 is a neutral ligand. Neutral means 2 electrons. So 2 into 2, 4. 4 is given. CO again 2 electron given. And now, because until now you did not take care of the charge of the complex, now you have to take care of the overall charge of the complex. Overall charge of the, without thinking what is the metal charge, what is the ligand charge, all of this thing you don't think. Now directly go to the overall charge, which is +1. Put +1 means it is electron count. So 1 electron will be less. So -1, that means, right? So now you see it is coming 16. And why it should come 16? Because it's 4 coordinated. 4 coordinated means there will be participation of only 4 d orbitals, not the 5 d orbitals. That is what it is expected and that is what it is finding. Understandable? Now, the next one. Iron means without thinking 8. Now, beta 5, again I don't think. 5 is the electron number into 2. So that means altogether it is 10 plus 8, 18. Without any fallacy, it is coming. And why it should be 18? Because it is bound by all the 3 dimensions. That means all the all of your x, y, z orbitals of the or oriented orbitals of the d has to participate. That means all the d5 d orbitals have participated into the bonding, and total number must be 18. The number is 18, so it is stable. That is the way to judge the stability of a particular complex, or it is often a popular question in case in all the complex. Basically, you can go to better to say in any of the exams now onwards, you will see one at least the question on this. At least one. Of minimum marks will be 4, maximum can be until 10. Okay, so that means you have to this thing, other thing you all forget, no problem, but you have to remember this thing very carefully. Now onwards, your competitive exam, your class exam, your assignment, everything. Okay, assignment I cannot say that what will be there, but each of your exam must be having a question on this. Minimum marks will be 4, maximum marks until 10. So remember this thing very carefully, and there is nothing much to remember. Negative charge, see whether it is bridging or not. Not bridging, 1 electron. Bridging, mu2 bridging, 2 electron. If it is, for example, now chloride is mu3, but how many electrons will come? Quick question. 5. Because two of the other metals will be having 2 plus 2, and because of the negative charge 1, so 5 electron, right? By this way you have to judge. If it is neutral ligand, then 2 electron. Look, but before putting this rule that 5 electron, you just see whether it is having 5 electron or not. Halides mostly have, but if it is CO, then there are a particular number of electrons which is present because of its try to draw its quick MO diagram and see how many non-bonding electrons are there. For CO, the number of non-bonding electrons are always 2, right? And that by this way you have to judge. But once you practice quite enough and follow this that 2 charts, I think it is quite easy, correct? And this is actually very easy scoring questions. Okay, fine. So, yeah, another thing is that often it is the case that students will come, sir, I put here 8, but here there was already I have taken care of the charge of the ligand, so why is no? Focus on only one counting method. Do not mix, okay, neutral and this thing together and then try to do something that will never match, right? Okay. And the charge count method are sometimes also called the oxidation state method because it is depending on the oxidation state because of the, ask something? Because of the oxidation state, because of the charge, it will be basically depending. So because of that, it is like that. Okay. Okay, so I will quickly finish. Next class will be here only, right? Sir is not. Is sir here? Okay, fine. We'll continue until sir come. Okay. So again, as I said, the electrons, very specifically, it is written how many electrons will be donated. All of these things. Then a few more examples are given. These are easy to follow. Okay, follow it from your end. हाँ सर, आपका क्लास है ना सर? Okay, now only one last example I would now describe. Basically, if you have, for example, mu2CO9. Now, there are 2 metals. How you will calculate? Nothing you have to see on. Just put 2 for 2 of this one. But in this case, what only you have to see is there a metal-metal bond. If there is a metal-metal bond, you have to take 1 electron extra. Or depending on how is the metal-metal bond. If it is a triple bond, 3 electron extra. If it is a double bond, 2 electron extra. Right? By this way, if you follow, it will be again coming the per metal to 1 electron. That means bond needs always to I made a mistake. A bond always needs 2 electrons. That means 2 electrons you can put together and then you divide it by the number of metal ions here, right? Then it will be equals now it will come 36 electrons divided by 2 because of the 2 metal will be coming to 18 electrons. Okay. Fine. In this above example also, you can see, you can calculate that also it should come that at 6 electron. Fine. अभी कौन सा क्लास है अभी? Which classes? हाँ, कौन सर है या मैडम?
लाल बहादुर सर.
Oh, Lalwal sir. Okay, sir is not here, right? Let me check.
सर लिंक आ गया है क्लास का.
लिंक आ गया सर, क्या ऑफलाइन लेंगे ऑनलाइन लेंगे पता नहीं, जो ही है. हाँ ठीक है, मैं तो खत्म कर देंगे अभी. ठीक है. अच्छा, these are different complexes. We will see one by one all of these things, or you can also look at your from your end. Okay, so how to determine the number of metal bond, that will be we will be talking in the next class then. Okay, from the 18 electron rule only we have to determine. Okay, fine. So this is one only caution, that these are the drawbacks of this 18 electron rule. 18 electron rule is a rule, not a law. A rule and law difference is that a law means is a universal, but rule means might be there are some exceptions, and you should be aware of those exceptions. Correct? And this is basically a formalism. That's why it is told. In many cases, if the coordination is lesser than 4, okay, lesser than 4, then it is very dangerous to apply the 18 electron rule. There might be it is not actually following it, okay, because even not the 16 electron it might follow, because sometimes it may be even 14 electron is stable. Okay, so that will only be happening if your number of coordination is very low. Like for example, 2 coordinated, 3 coordinated, then you have to be very cautious before putting this rule. Good. Okay, there are some exceptions. You can read the exceptions. Okay, fine. So with that, we will today's basically lesson was the 18 electron rule. Okay, so you can read it. I will send you the this PDF. Fine. Then this is the end of today's class. Bye.
Thank you, sir.
Thank you, sir.
Okay, bye.